Today I will discuss the quantitative use of porosity for reservoir estimation or reservoir reserve estimation. This process of estimating oil and gas reserves for a producing field continues throughout the life of the field. There is always uncertainty in making such estimates. The level of uncertainty is affected by the following factors: reservoir type, source of reservoir energy, quantity and the quality of the geological, engineering and geophysical data, assumptions adopted when making the estimate, available technology and experience and knowledge of the evaluator. The cross plot shows the relation between time and range in reserves estimates, and the upper axis or the above explanation is delineate the exploration process and production process. We can conclude that the exploration process or during the exploration process time increase, but there is no output, no extraction from the reserve. So our reserve is still virgin. But while entering the producing or the production process, we can find that the upper limit of estimate and the lower limit of estimate, that this upper limit and the lower limit explains the range of estimator about the reserve. This upper limit and the lower limit still converge until be merged as the ultimate recovery factor. The recovery factor is the percentage of the extracted oil from the reservoir or extracted hydrocarbon. This percentage cannot be 100%, but we want to increase it as much we can. Methods of reserve estimation. We have many methods or multiple of methods for reserve estimation, but we will throw the light on the Varia Metric method. Varia Metric method depends on porosity, net thickness, areal extent, hydrocarbon concentrations, and we can use the Eisbach map for compute the bulk volume of the. Okay, to calculate oil originally in place or oil in place, we need to describe each element in this law. I will start with VB. VB is the volume of the reservoir, and we can get it by multiply this constant by the area to the thickness. Porosity of P of T. Porosity of P of T. That means that porosity will change by changing pressure, and the pressure will change during time. Because we extract oil, so we reduce the pressure in the reservoir, so the porosity will change. By the same meaning, we can describe this P naught of P of T. P naught is the formation volume factor. Formation volume factor, it is a percentage that describes the change in volume of oil under the surface or at reservoir pressure, with respect to the change in the volume on the surface or our atmospheric pressure. So as time change, or during the time or during the production process time, the pressure will change, and so P naught will change. As well as water. S water, 1 minus S water, it is related to the oil saturation, and it will change with time. But at the original pressure of the reservoir, the only two fluids that are present in the pore spaces is water and oil. But by production, during the time, we will reduce the pressure, and the gas will start to get out from the oil to form SG. SG, it will be the saturation of gas. So this part of flow will change to 1 minus SW minus SG, because the gas will start to appear. This is the same law for gas in place, but we change also only the BG, the formation volume factor of the gas. Okay, so there is a very important question about what will happen for the volume of gas and oil from changing their positions from reservoir pressure to surface pressure. Simply, any gas will go in all directions. So the gas will have an increasing in its volume by reducing the pressure, but oil will have and decreasing in its volume by reducing the pressure. And this is causing because bubble effect curve. When the pressure will reduce from the fluids, the bubbles started to get out from the oil, causing the volume to be reduced. Now I will describe the drive mechanisms. To get a gas out, or an oil, or any hydrocarbon, we need a drive mechanism. Drive mechanism is something like will compensate the mething or the reducing in pressure with time. When the pressure will decrease, the fluid started to be static in their position. But by presence of solution gas above the hydrocarbon can expand it, and pressure or stress on the reservoir, on the oil, to make him get out, or presence of water below the oil fluid can drive the hydrocarbon fluids out. And there is a combination drive. Combination drive mechanism can be a combination between water and oil. Water and gas. So I will start by solution gas drive. The principle of solution gas drive or depletion drive is the expansion of dissolved gas and liquid in response to a pressure drop. The change in fluid volume results in production. Dissolved gas reservoirs typically recover between 5 and 25% of oil in place, and 60 to 80 gas in place. This diagram shows the four drive mechanisms. Gas cap drive, we can find that the upper part has gas, and gas will expand it by reducing our pressure. This is our well. So as we reduced oil, gas will start to expand to pressure or stress on the oil beneath it to force it to get out. We can find also that the gas oil contact started to go down. Okay, this is a cross-section view, while this is a map view. Now I will discuss about the reverse or the inversely one, natural water drive. Water is higher in density than oil, so we will find water below the oil, and as the production increase from the well point, the oil water contact started to go up. It is inversely processed. In terms of gas cap drive, yeah. The third one is the solution gas drive, where the solution is dissolved in oil, reducing its density and its gradient pressure also will be higher. So the gas that dissolved in the oil will drive the oil to get out from the reservoir. Compaction drive reservoir is a mix between gas cap and natural water drive. Finally, this cross plot shows a change in reservoir in reserve with respect to pressure and water cut through the time. So we can find in the solution gas drive history rapid and continuous pressure drop, and the rate of decline falls at bubble point pressure. Bubble point pressure, that means that this drive mechanism, which depends on the solution that dissolved in the solution gas that dissolved on the oil, will come out from the oil to leave the oil go out by itself. So the solution gas oil ratio low until pressure equal bubble pressure, then increases to maximum and declines absent or minimal water influx. So in this drive we can conclude that we will find a very or higher percentage of oil at earlier time, but throughout the time this percentage will decrease rapidly and the gas will come out and leave oil under it, which make what we call gas cut. While in the natural water drive or gas drive, not solution gas drive, okay, we can find that there is no rapid declination or increasing or reducing for pressure, and the pressure remains high, small drop, and the solution gas oil ratio remains low, and water cut will not happen if you still produce by your certain limit, and the residual oil may be trapped behind the advancing water. Our task was about calculating oil in place by the volumetric method. We have these inputs. So I will start it by divide the problem into several stages. The first one is we need to calculate the initial oil in place by using this law. Okay. First of all, I will calculate VB. VB is the volume of the reservoir, so it will be constant in all the stages. VB is here, porosity is here, 1 minus water saturation is here, and PO. So we have different types or different POs. PO at PI, initial pressure, PO at abandonment pressure. What's the difference about initial pressure and abandonment pressure? As I explained before, PO is the formation volume factor and it is related or function of pressure. So we have an initial pressure before we producing any oil, but after producing some oils, the pressure will be abandonment pressure and it will reduce to be 300 psi. We calculate the initial oil in place in initial reservoir pressure, so no problem in this. So we have 266 million STP. Every HM is 10 power 3. So we have 10 power 3, 10 power 3, 10 power 6 million. Okay, oil in place after volumetric depletion to abandonment pressure is given by this law. What's the difference between this law, the first one, and the second one? Okay, as I explained, after time, pressure will reduce, and we can reach to the bubble pressure. Bubble pressure means that the bubbles or the gas started to come out or get out from the oil itself, causing the presence of 3 different types of fluids: saturation of gas, saturation of water, and saturation of oil. So 1 minus saturation of water and saturation gas will give us the saturation of oil only at the abandonment pressure, and BO also will change, but VB and the porosity is still constant. So this is the value of oil in place in case of abandonment pressure. Now I want to calculate oil in place after water invasion at initial pressure. If we have give the reservoir water, so we will increase the pressure again to certain limit. What's the limit? By logic, we will increase the pressure to be at the initial pressure, because if we increase this limit, we can affect it badly and break the reservoir. And if we increase the pressure below this limit, we can not get all we can, and the recovery factor still can be higher. So oil in place after water invasion at initial reservoir pressure is given by this law. We can find that PO started to come back 1.68 like in the initial pressure, and residual oil saturation is get directly, and we can get the oil in place after water invasion. So number 4, oil reserve by volumetric depletion. Reserve, that meaning that I can get it out at any time. So in the initial pressure, the amount of pressure that maybe come out by just digging the reservoir, it represents Ni minus N1. So before the exploration, before the production, all the oil in place was 266, while after abandonment 148. This represents the amount that still remains, that's still in the earth, under the earth in the reservoir. So at the initial I have 266, and after time I have 148. So how much I get out is 118. This amount can get out by the initial pressure. So the recovery factor in this stage represents the amount that I can get out from the total amount, 118 divided by 266, which represents the initial oil in place, equal 44%. Number 5, oil reserve by full water drive. So I will give it more water, more pressure, and increase to initial pressure again. So from 266, still 97 remain in the pores. So I get out or explored or produced 169 STP, and this amount represents 64 from the all amount of the reservoir. So we can notice that the recovery factor be higher by increasing or changing the driving mechanism. The discussion of the results for oil reservoirs under volumetric control, no water influx, the produced oil must be replaced by gas, the saturation of which increases as oil saturation decreases. If S gas is the gas saturation and BO the oil formation volume factor at abandonment pressure, then oil in place at abandonment pressure is given by the law N equal Vp times porosity times 1 minus S water minus Sg over the formation volume factor of oil. On the other hand, for oil reservoirs under hydraulic control, where there is no appreciable decline in reservoir pressure, water influx is either edge water drive or bottom water drive. In edge water drive, water influx is inward and parallel to bedding planes. In bottom water drive, water influx is upward, where the producing oil zone is underlain by water. In this case, the oil remaining at abandonment is given by N equal Vp times porosity times reduced oil saturation over the initial formation volume factor. Thank you.